Okay, so this is video 7. I might break this up into 2 videos. So this may be the beginning of 7A. Remember, we're talking about limiting reactant problems where one of the reactants is going to get used up and that's going to stop the reaction. And there's 3 different ways of doing these problems. The first way is what we learned in video 6, and that's with comparing how much you need of reactant 2 versus how much you have of reactant 2, just to check to see, do you have enough reactant 2 to use up all of reactant 1? There's 2 other ways of doing these problems, and the first way we're going to see here, which is doing the stoichiometry problem 2 times, starting with each reactant, and then the one that produces the smallest product, that is the correct answer to the problem. And the reactant that produced the smallest amount of product is the limiting reactant. So I'm just going to scroll back up to one of those pictures that we were looking at, right? Let's see. So if I look at this, and here's the analogy here. If I had 8 car bodies, what is the maximum number of cars that I could make? That would be 8 cars. If I have 48 tires, what is the maximum number of cars that I can make, right? And so that would be 48 divided by 4, which is 12. So if I use all these, I could make a maximum of 12 cars. If I use all the car bodies, I could make a maximum of 8 cars. So what that means is I'm going to make 8 cars and then it's going to run out. I can't make 12 cars. So see how I just converted them both to products. Whichever one made the lowest number or lowest amount of products, this is the answer to the problem. How many cars can I make? And the reactant that gave me that answer is the limiting reactant. So now let's go do this problem. What mass of sodium oxide is produced when 25 grams of sodium reacts with 50 grams of Fe2O3? I'll just rewrite the balanced chemical equation up here. 6 sodium plus 1. You know, we don't usually write the 1, but we will use that coefficient. 3 sodium oxide and 2 atoms of iron. Okay. So what mass of Na2O is produced? So circle the do. 25 grams of sodium is reacted with 50 grams of iron. So if I'm going to use this method number 2, right, I'm going to do the stoichiometry problem twice, starting with each reactant. So 25.0, ooh, it isn't actually 25.0, is it? It's 25 grams of sodium. And now what I'm going to do is I'm going to try and answer the problem. What mass of Na2O? So then this just turns out to be something from way back a few weeks ago, just a regular 3 parentheses stoichiometry problem, right? First thing I'm going to do is convert to moles of sodium. Then using the coefficients from the balanced chemical equation, 6 moles of sodium will produce 3 moles of Na2O. And then 1 mole of Na2O has a mass of 61.98 grams. So, so what this problem is saying is if I get to use up all of my sodium, then I will be able to make, and it comes out to be 33 point something. So just to 2 significant figures, it's 34 grams of sodium oxide. Right, just double checking my good stoichiometry here. My grams units, my moles units cancel out. This guy has 2 significant figures. Any numbers from the periodic table have 4, so that's why my answer just has 2. And remember, it's only the middle mole over mole parenthesis that uses the coefficients from the balanced chemical equation. So I know that if I use up all my sodium, I'll be able to make 34 grams of sodium oxide. What if the iron 3 oxide is the limiting reactant, right? If I could use up all my iron 3 oxide, how many grams of sodium oxide would I make? So this is just another 3 parentheses stoichiometry problem. And, right, so first thing, 159.7 grams, and then 1 mole of Fe2O3. This is going to be 3 moles of Na2O, because the question I want to ask, right, in both of these stoichiometries, in both of these, set of dimensional analysis parentheses, I'm answering the same question: what mass of sodium oxide? So what you'll notice about these is that 61.98 grams, is that the last 3 parentheses, like this and this, because are the same in both problems, because I'm trying to answer the same question: how many grams of Na2O? When I do this one out, I get 58.2 grams of Na2O. So one thing that's really important when you do this problem, or when you do these problems like this, is that you are very clear about what your answer is. Because if you just leave it like this, I don't know what your answer is. Is your answer 34 or is your answer 58? Now, remember, the reaction stops when one reactant gets used up. So this says when I don't want to do that. When I use up all of my sodium, I will make 34 grams of Na2O, and the reaction stops. So what does that mean? That means, right, we always choose the lowest number, the smallest product. So 34 is less than 58. So 34 grams of sodium oxide is the most sodium oxide that I can make. And which reactant is the limiting reactant? Was the reactant that produced that. So if the question asked me, what is the limiting reactant? The limiting reactant would be the 25 grams of sodium. Okay. Now, here's another question that I'm often going to ask with these is, what mass of excess reactant is left over, right? If we go back, I'm going to scroll back up. I know it's kind of dizzying, right? There's always going to be a reactant. Whatever reactant is not the limiting reactant, there's going to be some reactant left over, right? In our car example, we decided that this guy was the limiting reactant, right? Once the 8 car bodies are used up, we can't make any more cars, which means we're going to have some tires left over. How do I know how many tires I have left over? Anytime that we're asking for excess or leftover, those two mean the same thing. I'm always going to use this little mnemonic device. So start, the S stands for start, and the U stands for used, and E stands for excess. Right? So in this case, I started with 48 tires. How many did I use? Right? I used 8 times 4, which is 32. And then how many tires did I have left over then? That would be 16, right? So what we're going to do is we're going to do that type of calculation, but with actual numbers. Let's make this so it's, this makes it a lot easier. Okay, so what mass of excess reactant is left over? So the first thing that you need to do is, well, what is the excess reactant? In the last problem, I just figured out that sodium was the limiting reactant. So that means that the other reactant, the 50 grams of Fe2O3, must be the one that's left over. So I'm going to do, start minus used equals excess, right? Leftover means the same thing as excess. How much did I start with? I started with 50.0 grams of Fe2O3. When we are subtracting or adding compounds, they need to be of the same compound. You can't add, what is 6 apples plus 3 pears? That doesn't, right? That doesn't work. But I said, what's 6 apples plus 3 apples? Oh, that's 9 apples. So when I subtract the used, the unit has to be also grams of Fe2O3. What I need to find out is how many grams of Fe2O3 I will use when I also use 25 grams of sodium, my limiting reactant. Once we figure out that this is the limiting reactant, that's our starting point for any stoichiometry problem with this, any stoichiometry question within this problem. So I'm going to start with my 25 grams of sodium. And where do I want to end? I want to end with grams of Fe2O3. So start my stoichiometry problem the same way as before, converting to moles of sodium. Then I use the coefficients from the balanced chemical equation. 6 moles of sodium will react with 1 mole of Fe2O3. Convert back to grams. 1 mole of Fe2O3, 159.7 grams. So when I calculate that, I'm going to get 28.9 grams of Fe2O3 left over, or excuse me, that's how much I'm going to use. So this is going to be minus 28.9. So now actually do the subtraction here, and I will get 21.1 grams of Fe2O3 left over. Okay? So that should be how much excess Fe2O3 I have. Okay? So I'll make this video because I don't want this to be too long. This is sort of video 7A. 7? Yeah, 7A. And then I'm going to show you the third way of doing these problems in 7B. And that will, and that should, I guess, that should give you all the 3 different ways of solving limiting reactant problems, and then you can work on homework problems 26, 27, and 28.